Okay, well, according to my clock, it's 2 p.m. here, which I think means it's 10 p.m. where Ofer is in Israel. So I think we'd better get started. It's my great pleasure to introduce our Vamos speaker for the day, Ofer Firstenberg. So first of all, I'll mention those of you who've been following Vamos for a while know that we started it during the pandemic when we didn't have other opportunities to have seminars. And I think in part because of the difficulties associated with the time zones and the fact that 10 p.m. on a Friday is not such a great time. Actually, Ofer was one of the founders of a sister seminar series, the Quantum Science Seminar, that sort of served our European and Asian and then Israeli colleagues. But so it's a pleasure to have him giving a talk here at Vamos. So Ofer got his PhD at the Technion before coming and doing a postdoc at Harvard and MIT, which is where I had the pleasure of overlapping with him and learning a lot from him. And Ofer, while during that postdoc with Misha Lukin and Vladan Vuletic, sort of did some really field opening experiments on sort of generating effective interactions between photons using Rydberg atoms. And I think since going back to the Weizmann Institute to be a professor in 2014, Ofer's continued that work, and I think that's what he's going to tell us about today. The last thing I'll say is that in addition to all of his many sort of scientific accomplishments and contributions, Ofer is a man of, I think, many interests and talents. And if you're ever at the Weizmann Institute, you should have him give you a tour of the community garden that I think he was instrumental in establishing, and where he grows some beautiful vegetables and things like that. So anyway, take it away, Ofer.
Thanks, Shimon. And hello, everyone. So let me start by showing you what happened about 5 months ago in one of our group pool parties. So what you see in here is actually me holding this kid's surfboard. This is a bit, all right. And here I'm pushing the water, the surface of the pool. All right, sorry, it's too noisy for me. All right. And you see these two features that form. These are vortices. This is a pair of vortex and anti-vortex. You see by the direction in which they rotate. They look pretty stable. They are actually stable partially because they are connected underneath the water, the surface, with this vortex line, an arc. You can try this at home if you have a pool at home, or you could look for one of those many YouTube movies that show that. Pretty amazing how stable they are until they get eaten by this turbulence. And as you know, vortices are prevalent in physics, and we find them in many, many systems, in water, in hydrodynamics, also in space and the atmosphere, in condensed matter, in quantum fluids, in ultra-cold atoms, Bose-Einstein condensates, and also in optics. And in optics, they manifest as phase twists of the electromagnetic field. So actually the phase going from 0 to pi and then to 2 pi, usually associated also with a 0 of intensity in the center due to this phase singularity. And they have been around for some time, probably 30 years back. This is the first observation in 1989 of vortices. And if you want to read about the story of vortices since then up till today, I recommend this recent review paper. And so they are very well studied. And also myself, I worked a bit with vortices. This is what you see here on the right. So these are vortices with charge 1 and charge 2. And this is actually vortices that are imprinted on atoms, on diffusing hot atoms. We did this with this storage of light technique. And if you let the atoms diffuse, you see that the vortices diffuse, so they smear, but still maintain their dark center because of the singularity, the topological defect that cannot unwind due to diffusion. Now, in this example, but also in all of these examples, the vortices are generated by matter, by some material component that imprints the vortex on light. For example, this holographic phase mask, where the phase imprinted just goes from 0 to 2 pi, or some other way to imprint this discontinuity, dislocation on a static mask or on a digital special light modulator. Let me change the way I share the screen. And so if you think about matter imprinting vortices on light, this can a bit like a carousel in a playground, where essentially the carousel rotates and you can put as many kids as you want on it and as many children as you want, and it will rotate them, right? So these are kind of the photons that rotate. But we are after something different. We are interested in a scenario in which these vortices are imprinted by light acting on light, so something like that. And when light acts on light, this is the realm of nonlinear optics. And indeed, there are a few examples where nonlinear optical systems show the generation of vortices without any matter that imprinted at vortices. So this is probably the first observation of vortices in a nonlinear material. This is in fact light propagating in an atomic vapor. This is an example with a polariton superfluid. And in these examples, because these are standard classical nonlinear material, you need a lot of photons, millions or billions of millions of photons in order for the nonlinearity to be strong enough and generate a vortex. And we are after a scenario, an extreme one, where a single photon, or if you want a pair of photons, are enough to induce this vortex. So we look for an interaction, an effective interaction between photons that is strong enough on that level. And this brings us into this regime, to the limit of quantum nonlinear optics. So let us dive into that. We'll try to quantify how much strong the interaction needs to be. The way we are going to do that, we are going to examine this medium and we're going to send this very simple state of light into it. So you see here a state with mostly 0 photons coming in, and sometimes 1 and very rarely 2. And in fact, epsilon here is the electric field, the amplitude and the phase of the electric field. This is a classical state. This is the state of laser light, a coherent state, but a very weak one. And after going through the medium, we expect to see this. The medium would have some absorption and some phase. This would be the linear response, and which is marked by eta and eta square in here. And if the medium is nonlinear, then there would be some extra factor here, psi, which would be different than 1. So 2 photons will experience a different optical response than 1 photon. The medium would be quantum nonlinear, strongly nonlinear, if psi is very different than 1. And these are 2 examples for media that are quantum nonlinear. Here, psi is very small, say close to 0. And so the medium transmits single photons, but does not transmit pairs of photons. So it's a single photon transmitter, very strong nonlinearity, a dissipative one, it scatters photons. And this is a pretty useful device for quantum information processing. And an even more useful device would be the other one, in which psi in absolute value is still 1. So all photons pass through, but the phase of psi is different than 0. And ideally, it is pi, which is the maximum that you would want. So this device, a conditional phase of pi, would, for example, maximally entangle photons that enter it in the form of photonic qubits. So this is how strong we want the nonlinearity to be. We want this psi to be very different than 1. Now, psi is a physical quantity that we can measure. And it's very simple to measure. You simply split the light field and put 2 single photon detectors and collect photons and calculate correlations. This is the well-known G2 correlation. It's a normalized version where we normalize the denominator, the probability to see 2 photons by the probability to see 1 photon square. And if you plug in these 2 amplitudes, you immediately see that G2 is exactly psi square. Okay, and here it is measured with respect to the time difference between the photons. It is the standard procedure. Look, for example, at the blue curve. The blue curve represents a scenario in which 2 photons prefer to come together. They are bunched with respect to what you expect from classical light. This is for the absolute value of psi, and we can also measure the phase of psi, so characterize the full psi. And the phase of psi we measure by interfering the photons with a local oscillator that comes around the system, kind of like building an interferometer. And you see here measurements of psi, the absolute value, and the phase versus the time of arrivals of the 2 photons. So that's psi outside of the medium. We can also generalize psi and think about some probability amplitude to find the two photons inside the medium. So here it's the probability amplitude to find one photon at coordinate z1 and the other one in coordinate z2. So for the more formal definition, if you're inclined to that, this would be the this coefficient of the two photon component of the field. Now, psi, you can think about this a bit like a wave function. It behaves somewhat like a wave function for the two photons. It is not exactly the wave function, but it feels like a two-body wave function of matter. And to allude to that, we would draw those cartoon where you would have a psi versus psi. It's a bit like matter, but not exactly the same. And we need to understand this psi. So let us look at typical dynamics so that we get some feeling. So here is a psi drawn on these two coordinates, position of first photon, position of the second photon. Psi in the origin starts at 1. That represents the Poissonian distribution that says that no matter where the first photon is, the second photon is equally distributed in all other times. And they enter the medium and they propagate more or less in 45 degrees each, with its own velocity, but kind of more or less the same velocity. Now, if the interaction between them, the effective interaction between them introduces some extra phase, then we can think about this conditional phase a bit like a potential that acts between them, so that photons that propagate together and they are close in space would acquire extra phase compared to photons that propagate far from each other. Okay. And if this is ideally, does not have any dissipation in it, but only phase, then we expect nothing interesting to happen in the probability. In addition, in every optical system, and also in ours, there is some optical dispersion, some linear dispersion. And this linear dispersion would smear features, optical features. So features could not stay sharp, but rather there would be something that will disperse them. So then you would expect less phase to accumulate, but kind of dispersed and occupy more space, and there would be starting to be something interesting happening in the probability. Okay? You probably already guessed by now that if I have a potential and I have something that looks like mass, this dispersion, then I can maybe write this sort of like a Schrodinger equation, effective Schrodinger equation, where instead of time, I have this center of mass coordinate of photons propagating together in the medium, and then some mass term and a potential term. So you see, they do act somewhat like a wave function. All right. So that's the formalism. How do we achieve such strong effective interactions between photons? We use polaritons, and we use polaritons that excite Rydberg atoms. Okay, so we kind of let stuff propagate in an atomic medium and generate those polaritons. So let us look a bit into what polaritons are and what Rydberg atoms are. So here is a polariton. I hope the animation works well. We have a pulse of light that we send into the medium, and we send it into the medium under the conditions of so-called electromagnetically induced transparency. Our signal light is resonant with this excitation from the ground state to an excited intermediate state, and then we also have a strong control field, classical field, that couples the intermediate to an excited state. And under these conditions, this very famous phenomenon occurs EIT, in which light is transmitted. But it is transmitted while exciting the atoms. And for each photon that propagates, actually there is one excited atom. And if we use a Rydberg state, that would be a Rydberg atom excited. And this Rydberg atom plus a photon is a superposition, kind of a hybrid creature that we call polariton. And because we excite atoms, the photons slowly propagate. This is sometimes called slow light. And in our experiment, the groove velocity is about 1,000,000 times smaller than the speed of light in vacuum. So photons come in and they squeeze and they become very, very small in space, and they get tightly close together because they propagate slowly until they leave from the other side. And for our photons that are about, say, a microsecond long or hundreds of nanoseconds long, they become as close as 10 microns. 10 microns is close enough to get some interaction between atoms. We work with Rydberg atoms, that are now very famous because they are, the workhorse of quantum computers that are based on neutral atoms. These are states of atoms in which the outer electron occupies a very highly excited orbit. We use n equals 100 or so. And then two Rydberg atoms, because of the very physically large orbit, have a strong dipolar interaction between them. We employ the van der Waals interaction between them that scales very, very fast with n. So imagine how large this number is for n equals 100. And it is large enough in our case to be significant at 10 microns distance. We'll explain immediately why. So getting polaritons that are actually Rydberg atoms that propagate, we imagine this scenario of two photons propagating together. One is a happy polariton. It is transmitted well under EAT. It excites a Rydberg atom. And then the second one that is nearby is not that happy. Because of the interaction between the two atoms, the second photon is not allowed to excite a Rydberg state. This interaction shifts, the van der Waals interaction shifts this state. This is called blockade, Rydberg blockade. And due to the blockade, the second photon that is nearby is actually trapped within this two-level system. And so because it is on-resonant, it will scatter, or it will acquire phase, or both. And this is the interaction that we are going to use. So we have a happy polariton and somewhat a blocked photon. And this all happens within a range that we call the blockade radius. For the experts, that would be the where this interaction is equal to the EAT line width. So that happens on about a 10 micron distance. So before I show you how the experiments look like, I want to mention that we can actually, despite this fact that this looks pretty complicated, we know how to theoretically describe it very well, and numerically we can actually calculate this fully. To give you a sense of how this is done, we have a space, say a one-dimensional space along Z. We can create a Rydberg state somewhere in this state. We can create an excited atom, or we can simply have the photon. So these are epsilon, p, and s. And we can write the full Hamiltonian, which is very simple. This is that, coupling the states and coupling the photon to those atoms. And the eigen states or eigen branches of this Hamiltonian are actually the dark polaritons, these hybrid creatures of a photon and atoms. So this is very well known. And then the interaction between two Rydberg atoms is just represented by putting this interaction term whenever we have two Rydberg atoms nearby that are excited. And this can be solved at least for 1, 2, and 3 photons fully on a computer. And for more than 3 photons, that becomes a bit more complicated. You notice that this Hamiltonian has these polaritons as a solution basis, whereas the perturbation, the interaction, is diagonal in some other bases. So you can think about this kind of like a scatterer. And then you can invoke scattering theory and effective field theory to describe what happens to that in the more than 3 photon level and few body levels or many body level. And these papers derive that and solve the low energy behavior of this system. So this is very useful. All right, that's the theory. What do we have? So here is how the system look like. We trap ultra cold atoms in this elongated cloud, elongated dipole trap. We get to about 50 microkelvin, and we focus light tightly onto this cloud, so tight, 3.5 microns waist, so that the blockade radius, the range of interaction, is much larger than the focus, which means that we are effectively in a one-dimensional scenario. The cloud is very long. It's the optical depth is about 120, so that's pretty high, and the density is high. It's on the order of 510 to the 12. So that allows us to get a strong and long, effectively long interaction. We have detectors, of course. When we correlate two detectors, we can measure G2. These are data showing you bunched photons and anti-bunched photons. We have another detector to measure the phase. When we mix with the local oscillator, it's kind of interesting how this looks like in the raw data. You see, these are the bit note look like, and this is how the bit nodes look like if I condition these measurements on detecting another photon, say in detector 1. So you see that the bit nodes shift a bit, and you can measure how much phase this entails. And in any experiment, we could also add another detector so that we can simultaneously also measure G3 and phi3 and get all of that for free. Okay, and before we are diving into results, let me break here and see if there are any questions.
Okay, so we have a couple of questions. Christian actually was wondering, in the limit of ultra-high powers, no medium is required to engineer photon-photon interactions, I guess pair generation. I wonder if there are some vortex-related phenomena to be expected in this extreme limit. Maybe you thought about this exotic scenario at some point.
That's a good question. So indeed, in vacuum, maybe not on terrestrial land, but on very, very high intensity, there would be photon-photon interactions. There are people trying to do this on Earth. And if the same phase, as you will see, I didn't still show these vortices, you will see it's a very basic phenomenon, this vortex generation. It's because of this topology and because it stems from kind of standard Schrödinger components, you might as well expect this in vacuum. Yeah.
Okay, maybe this is a very sort of simple and naive question, but when you started motivating this whole thing, you gave the example of a very nonlinear system being as something that sort of absorbs all but one photon, for example. But it seems like actually the easiest maybe nonlinear system to make is the opposite case, where you have one atom and it absorbs only one photon and then transmits all other photons. Can you give some insight into whether that's sort of less interesting or less useful, or and how to think about that?
So I would say, for first, actually, we can do that now with our system. So I maybe show this in a very, very last slide. This is a scenario that is the typical one in waveguide quantum electrodynamics. You would have a single emitter coupled strongly to some channel, and the strong coupling, represented by very high cooperativity, would mean that each and every photon that comes through this channel is absorbed by the atom, but of course this atom can absorb only one photon, and then all the rest will propagate. And we know that waveguide quantum electrodynamics are very useful systems. For example, for realizing optical quantum information processing. So yes, essentially this single atom or effective atom, super atom that is strongly coupled to a channel is extremely useful. Yeah.
Great. And then maybe one more question. I guess in the pictures that you described, you kind of described it as if you have, maybe one photon and then another photon coming in sometime later. But I guess in reality, I think in most of these experiments, you're working with weak coherent pulses where you don't actually have one photon, but you have some kind of combination of 0, 1, 2, 3, etc. Can you maybe comment on, how this changes things, or if this changes things?
So excellent question. So in the experiments we did up until now, indeed, we didn't use any quantum light as an input. We only put in classical light coherent states, and they left as very, very quantum. And this means that we rely on statistical measurements on photons that have propagated through the system, and mostly we see nothing. So we use very, very weak incoming light. Sometimes we see singles. Most of the time we see single photons, and then rarely pairs, and even more rarely triplets, and in the very near future maybe 4 photons. We of course aspire to do that with quantum input light, especially if we are now going towards trying to realize actual gates, and then you need to do that with photons. It's kind of a bit hard to generate quantum light single photons with the requirements that we need, very narrow band and relatively long, microsecond long single photons. There are ways, but not trivial ones. Yeah, and this determines our signal to noise, the fact that we mostly work with zeros and ones. Yeah.
Great. Okay, well, I think with that, we'll let you continue, but I'll just remind everyone, you can ask questions using the Q&A function or over YouTube on the chat. Go ahead, Ofer.
All right, thanks. All right, so I'll take you now also to remind you how it works. Here is the gas of atoms, ultra cold atoms. We send photons through that. We imagine that they propagate. There is some range, the blockade radius, within which they interact, and the interaction look like this. We have one happy polariton that propagate, and another photon that is not happy, and it couples to this state. And let us first examine the dissipative case, where this second photon is resonant with the intermediate state, so it scatters. And here it's pretty easy to do examine the strength of the interaction. The strength effectively of the interaction is how well this second photon scatters. And this we can quantify by the optical depth of this sphere of size 10 microns. We call this the blockade optical depth, ODB. It's a unitless number, and it is the most important one in here. This is the one that determines how strong the effect of one photon is on the other. And if ODB is large, we expect a very strong effect. Here are kind of sketchy simulations. You see here the probability to see two Rydberg atoms. So indeed 0 when they are close enough. So blockade works well. And if you look at the probability to see photons, then at the beginning, the photons actually come together. But then very quickly, in the very beginning of the medium, they are absorbed because the optical depth of this blockade range is pretty high. So they are absorbed fast. And here is how data look like. So we send, again, a weak laser light from one side to the medium when we measure the statistics. And we observe under these conditions very strong anti-bunching. Photon pairs actually do not make it through together, only very, very, very few. This is for principal quantum number 85. ODB, this number is 10. And if you look at the size of this anti-bunching feature, it's actually very wide, much wider than what you would expect from the tiny blockade range. And the reason, again, is dispersion. What actually happens in the medium is that these sharp features do not maintain, and the field and also the atomic part of the polariton disperses. In fact, this is probably one of the highest anti-bunched range of any quantum light, and we can actually make it larger and probably get the largest ever anti-bunching range. Okay, so that was for dissipative interactions. We are more interested in dispersive interactions where we keep the photons alive. And we do that by detuning away from the intermediate state. So now instead of scattering, we would have the second photon acquiring phase. It is a bit kind of to the experts, but if you look at the spectra, transmission spectra of the through the cloud, you could see how happy polaritons look at see the medium, and how these blocked photons see the medium. And we choose to work at the point exactly where the transmission of both of these photons is the same. So there is no dissipative component to the interaction, but the phase that they acquire is very, very different. So this is kind of almost a phase-only interaction. And if the interaction is a phase interaction, then we expect the phase for two photons that propagate together to accumulate. In this particular synthetic simulation, it goes from 0 to almost 2 pi. Of course, no Rydberg atoms in between, and some bunching that comes with it. I would mention that, again, ODB, the blockade optical depth, is the most important parameter, and here it determines how much phase the photons acquire. Now here again, we have optical dispersion. Here it's actually very convenient to see the optical dispersion. This is this curvature. And so now we have an optical dispersion, a curvature, which we can translate into a mass term, as we kind of did in the beginning. We subtract the linear part and keep only the quadratic part. And there is a phase that two photons acquire when they are close by, and this determines the depth of the potential. And the width of the potential is the range of interaction, the blockade range. And we can then write this Schrodinger equation. And in fact, this is, although coarse, this is an approximation that you could derive from the full model of the system. And it's interesting, again, the time is played by the distance in the medium. And to quantify the strength of the interaction, we can look at this unitless parameter. It's a regular parameter in Schrodinger physics that determines how many bound states there are to the potential well. And if you look at this parameter, you see that again, it is governed by ODB. So ODB determines how strong effectively the interaction is. So this regime was first experimented with in Harvard when I was there with Lukin and Vuletic. And what we have observed is bunching of photons under these conditions. So this is the data. And this matches pretty well, at least qualitatively, what you would get if you simply integrate this Schrödinger equation. And to show you how the dynamics look like, we start here. We start with psi equal 1. This is the Poissonian distribution. And then kind of like a quench, we introduce the potential. And this potential then generates those ripples. And we associate the bunching with an effective attractive force. So you have a potential well, and you have a mass. And therefore, you should have a force. And this force pulls photons to the center to be together. It pulls pairs together, and it depletes those other parts, the outer parts. Also, at the area of the well, the wave function acquires extra phase, which is the conditional 2-photon phase. And in this work, we have reached this minus quarter pi or 1/3 of pi. And although this is not pi, it is enough to obtain entanglement, a deterministic entanglement of initially independent photons. Now, as you know, those Schrödinger dynamics are governed by bound states. So to understand how this works in here, we have a shallow well. It supports at least one bound state. Well, in this case, a single bound state. Here is the well. Here is the bound state that it supports. It's a shallow one, so the bound state extends away. The initial wave function is psi equal 1, and so at the beginning there we have some bound state, and we have a bunch of unbound states, other eigenstates of the equation that are unbound, and we will denote them as the scattering state. And to a coarse approximation, those scattering states can be simply written as 1 minus the bound state. This is everything that is not part of the bound state. And so to get an intuition of how this dynamics comes about, we would, in a very coarse but a very good qualitative description, we would think about the bound state as rotating with its energy, so rotating fast, and a bunch of scattering states, or a scattering state that doesn't change at all. And this is pretty good approximation because the energies for this type of scattering in the area of the well are very, very low. So it acquires phase very slowly. And the dynamics that we see here, these wiggles, are simply destructive and constructive interferences between the bound state and the scattering states. All right, this is for a shallow well with kind of a very quick dynamics. And we get this in our system when we work with OD, say, 50. So you see phase about 1/3 of pi in here, and pretty strong bunching, again, due to this attraction with pretty nice depletion. And now we increase the optical depth. So we let the system kind of evolve more. And at OD optical depth of 75, we reach this hallmark of pi conditional phase. And together with this pi conditional phase, we also get a very strong depletion in here. So that ideally would get to 0 at some point. So of course, if you use, for example, the system under these conditions, you could entangle photons in them into a maximally entangled state. It's actually pretty neat, again, to look at the raw data in here, and we see the conditional bits shifts totally, the crests getting into those valleys in here. So this is really like a conditional pi phase. And now we want to increase the OD even further. And thinking about this, I could ask you whether you think we would get that, so we could get even more phase, and more phase that is pulled kind of to the outer parts, or because this phase is minus 2 pi is 0 and minus 3/4 of a pi is pi half, would simply jump to the upper part of this phase, unwrapped phase. And the answer is that we get a second. So somehow the system let the center acquire more and more phase, but in order to agree with the outer part, it introduces some phase jump. And to see this more vividly, let me take those 3 curves and even many, many more curves and simply put them on one image. So you see here the data showing you the phase, the conditional phase versus the optical depth that we change between experiments. And you see that indeed the center requires gradually the phase from 0 to pi and almost to 2 pi. 2 pi is 0, right? And the outer parts are 0. And so the way they decide to agree is simply to at some point nullify this. And in order to do that, they introduce these 2 points, which if you go around, are the phase that runs between 0 pi and 2 pi. So these are a pair of vortex and anti-vortex phases in this artificial space currently, optical depth and time. At the point where we see the vortices, we also see the minima, ideally 0 of the function, which makes sense because the phase is undefined and this is a dislocation. And as I told you, we can simulate this system fully with the Gaussian cloud, and our simulation recover these dynamics very, very well. But what we can do in the simulation and we cannot do in the experiment is to look into the medium and inside the medium and see what happens. So let me show you what happens inside the simulation along this cut in this particular calculation. So this is the wave function, the phase of the wave function inside the medium. And what you can see are 2 vortices now in real Z1 and Z2 spaces. And these are 2 body vortices, a vortex and an ida vortex, that are stuck inside the medium. This dashed line represents the cloud periphery. So this is pretty cool. In this particular experiment, we would have 2 vortices inside the medium. It's also pretty neat to see how we see the phase jumps. The phase jumps come out of the medium at the point at the optical depth where the vortices appear exactly at the edges of the medium. So they are slightly outside and we see them, and with a bit of a smaller, a bit of a higher optical depth, they are slightly inside and we no longer see them. So this is pretty neat. And it turns out, as I said before, that it's a very, very natural outcome of the Schrödinger dynamics. So it's quite surprising. If you look at this very simple Schrödinger equation of a charged particle in a well, which we all studied in 2nd grade undergrad, or I don't know, in 11th grade in high school, depending on who you are, then it just pops out. You start with psi equal 1. At the beginning, you've got some phase accumulated and some bunching. And this is due to the rotation of the bound state around the scattering states. But then if you just simply continue, at some point you would get those vortices appearing in the Schrödinger dynamics. And simply they come about at the point where the bound state is exactly acquire the pi phase compared to the scattering state, so they destructively interfere. And although this is a sketchy approximation, you could see that when we solve the full simulation, the full Schrödinger dynamics, it just does this and periodically repeats itself. It's not exactly the same point because it's not exactly this one, but it's a very good approximation. And since we also know the full dynamics, we can calculate exactly when we expect to see those vortices. We put this on this phase map of optical depth, which we characterize with the accumulated phase, and the interaction strength, which is depends on ODB. In this region of space, we expect to see vortices. We expect vortices to appear. This is where our experiments are done. And this is this current status of the experiment, and these are the previous experiments. So obviously could not kind of reach the point where they see vortices. And it's quite easy to calculate this line, even with this Schrödinger dynamics, and even in a very, very coarse analytic derivation, you kind of get this. So it's natural. And now, finally, for 2 photons, let me go back to our pool and how we push photons around. So let me show you something kind of special. Up until now, all the experiments were our steady state continuous wave, but we can also simulate time-dependent simulation. So we take our cloud, which is empty, and we now send a pulse. into it. And I hope the videos show up nicely on Zoom. So you see how the vortices gradually generate. Similarly to the pool, there are some vibrations, reverberations, and eventually they stabilize and they just stay there and stay stuck inside the cloud. So before now I go to 3 photons, maybe that's another good time to stop and see if there are any questions again.
Okay, so Caden was wondering, in the plot showing G2 for the bound states, are the wiggles from interference reproducible, or do they shift shot to shot?
Hi, Kaiden. No, this is very reproducible. It's now that we know how to fully integrate the equations, even for our Gaussian cloud, it's a qualitative. There are qualitative agreements, and there is no. I mean, we take data for a few days, and it's a pretty reproducible result. Yeah.
Okay, a question from the audience. So what is the physical significance of optical vortices? Can you maybe give a little bit more physical intuition for how we should think about this?
We also think about this. I'll show you in a minute what 3 photons do, and I think this topology of vortices is actually a very good provide kind of an explanation for the role of the bound states in this the whole dynamics of photons in its nonlinear medium. Particularly, for example, if you want to generalize eventually to several photons, to many photons, and obtain some, for example, Kerr-like effect where you would accumulate pi per photon or several pi's per photons, then those vortices actually give you kind of a topological tool to predict or understand why you get what you get. I hope this would be clearer next. Other than that, we should think if there is like a deeper meaning to them. Yeah.
And then maybe I was wondering, so when you show this, kind of effective potential, and you show that you have a bound state, is it possible to engineer more than one bound state? Can you have like row vibrational levels of a photonic molecule or something? Or
yeah, sure. Let me show you again, maybe this phase map. So the second bound state for 2 photons would appear when square root of lambda is pi. So when lambda is about 10. Okay, so you see we originally we were here where lambda is much smaller than 1, and now lambda is much larger than 1, but it's still not 10. So we have some way to go, but we are close. However, as you will see, we have 3 photon bound state that kind of coexist with the 2 photon bound state. So that's already beginning to be like a forest of bound states. And even before we get to the second bound, there should be interesting stuff happening before it is generated, because also close to the scattering resonance, we know that things start to diverge. But it would be super cool to get to the point where now the second bound state appear. I agree. Yeah.
okay, great. I think maybe we can keep going.
All right. So we are proceeding to 3 photons now. And in fact, it's quite a trivial generalization. We simply need more another detector, and another channel in our photon tagger, and much more code and much longer analysis on MATLAB. And then eventually what we calculate is simply the probability to see 3 photons normalized by the probability to see a single photon, and the data look something like that. This is, for example, characteristic measurement versus the time difference between the first and second photon, and the time difference between the third and first photon. And we see bunching. So this is the bunching we already know, and some interesting feature right here in the center. Something we like to do, and we'll do from now on, is to move to coordinates where no photon is special. All of them are special equally, like your kids. And these are the Jacobi coordinates, where simply we have a 6-fold symmetry of all combinations of pairs being together. So in this coordinate system, we have eta that represent these equal distances between photons, and we have zeta, which is a pair separated from a third photon. But it's not really important to remember. As far as the formalism is concerned, again, quite a trivial generalization. We simply add 3 photons to the mix, and we look at psi3, the extra amplitude that 3 photons gain compared to what you would expect from linear transmission. Also, to measure phase, again, trivial generalization. We take our local oscillator and we now correlate with another detector, so we get phi3 and G3. Most of it has been done before, again in Harvard, after I left, actually, and they have observed the bounce state for 3 photons. So, for example, this is this feature that is both higher and narrower than what you would expect from only pair interaction. So there's kind of an extra juice coming from the fact that the pairs are all together. So we would expect the dynamics to be governed by something like that. Some bunch of bound states that will rotate, that will oscillate in their own energy, speed, frequency, kind of, and the remaining scattering state. And again, this would be now composed of 2 photon bound states, all 6 combinations, all 3 combinations of them, and perhaps this 3 photon bound state. So let's start by looking at phase data. So this is phi3, the conditional 3 photon phase, again put on the Jacobi coordinates. And at the point where we already know that the 2 photons acquire a pi phase, this is what we get. Outside of the, away from the center, we have pairs that accumulate a pi phase. And in the center, there is an extra feature that is 0, either 0 or 2 pi. We'll get to see this soon. That comes from the fact that there is now a 3rd photon joining the pair. This is at a certain OD. And as we did before, we can now look at data versus the optical depth for kind of different distances in the cloud. So these are, if you want, these are 3-dimensional cuts of, or these are 2-dimensional cuts of a 3-dimensional space of data. So you see, for example, versus eta, the distance between the uniform distribution of photons, the pair acquire a phase much faster than it acquires if it was only a pair. So the triplet acquires a phase and gets to pi, and then probably to 2 pi, and then again to pi, and then accumulates more and more. And if you want, I remind you, this is the data that we had for 2 photons, so you can compare this and that, and you see this extra feature coming from the 3rd photon. Now it's kind of hard to see what we get in the 3-dimensional space. So let me help you. What we do, we look for the points in the space where the gradient of the phase is maximal, and that gives us surfaces, and then we color those surfaces with the measured phase. So you see here data, the same data actually as in here, showing you the vortex structure. You see here vortex lines or tubes, and in the center, a vortex ring. This is a ring, and if you cut it, you see that it actually goes over from 0 to pi and to 2 pi back. And as I'll show you, we associate those lines, these ones, with 2-body interactions with the thing we already know, and the ring with a 3 photon bound state. So how does it look? Here, let's look at the lines. The lines come from 2 photon bound states. So I could take the sum of all combinations of photons, sum of 2 photon bound states, and then plug them here. They all rotate in the same frequency. If I take that simple solution and I eliminate, by hand for a moment the 3 photon bound state, then indeed, analytically actually, I get those vortex lines. So they are associated with those 2 photon bound states. Funnily enough, we can also do that experimentally. So not eliminate actually the 3 photon bound state, but we can take data of 2 photons, pair data from the pairs that phi2 data, and in a protocol that I want to explain right now, we can predict how the phi3 data, how the phi3 measurement should look like if there was only physics that come from the phi2 data. And you see that it's kind of more or less the same, only without the central feature. And if we cut this 3-dimensional space, we indeed get only the lines. So these vortex lines are associated with the 2 photon bound state that we already know. As for the ring, I now put back my 3 photon bound state, and this is a kind of a known ansatz for a structure of 3 photon bound state. It is simply an exponential decaying exponent in all 3 directions. So it only exists right at the center where the photons are together, and whenever a photon goes away, it goes to 0. It's a localized state. I can do the same trick now. I can ignore the 2 photon bound state and look at only the 3 photon bound state, and then indeed I get a ring. So again, in a Schrödinger equation of 2 dimensions now, if I take a localized bound state, it will generate periodically rings. This is the ring that we expect, and now if we sum them together and simply take the full solution of the Schrödinger equation, we get what we see in the experiment. So to summarize, those vortex lines and ring are associated with the 2 photon and the 3 photon bound states. How much phase do the photons accumulate? So back to this data. This is 0 or 2 pi. So to unwind this, to unwrap the phase, essentially it's pretty hard to do on this plane because it's not really clear going from pi to 2 pi, whether I should climb up or climb down. But in fact, this is again a 3-dimensional space, and I could use the other dimensions to unwrap the phase deterministically, and the unwrapped phase is in fact 2 pi. So 2 photons acquire pi, and 3 photons acquire 2 pi. Another way to understand this is to penetrate through the ring into the center, and then exactly at the center of the ring, you would get pi from the vortex lines and another pi from the ring, and therefore 2 pi. And interestingly, this is not what you would expect from a quantum Kerr medium. In a quantum Kerr medium, you would expect all pairs to interact such that 2 photons acquire pi and 3 photons acquire 3 pi, but we only see 2 pi. And partially this is because in this Rydberg polariton media, photons do not interact simply, and there is a genuine 3 photon interaction term that is due to the fact that 1 photon can block the 2 others, and then the 2 blocked one are not interacting. I wonder if maybe very quickly, let me show you the G3 data, the correlations. So you already saw that. We have a special feature here in the center. One common practice is to subtract from this G3 data the part that comes only from 2 photons, kind of predicted part, the disconnected part, and look at only the extra juice of 3 photon interactions. And indeed, this extra effect is only in the center. You see that this is a strong bunching effect. It's actually very strong. It's on the order of unity, coming from photons bunching together as a triplet rather than sum of pairs. And there is also repulsion in the center. And this is due to this genuine 3 photon interaction that I mentioned. So you could see this also predicted 6 years ago by Hans Peter and colleagues, where you see bunching and then depletion of the center. And this is due to overall stronger attraction, but extra repulsion. So that concludes my story about simple Rydberg polaritons. And before I wrap up, I want to mention kind of what other things we now do with this system at Weizmann. So we started experimenting with counter-propagating photons. This is pretty cool because up until now, we only had one mode, so one set of indistinguishable photons. And now we have 2 distinguishable modes, and therefore we can go forward and produce gates and entanglement. So we do this by simply generalizing the system, and it gives quite interesting results. You see here, for example, anti-bunching of the cross G2 that is much wider than the self G2, and interesting features here in the cross phase measurements. We also work now with 4-level structures rather than 3-level structures to generate polaritons that are based on P Rydberg states and rather than S Rydberg states. So this is G2 measurements showing you the P Rydberg polaritons. And we do that because we want to now combine our counter-propagation system with both S and P polaritons. So to get dipolar interaction between them rather than van der Waals. which would be much stronger and much more robust. And finally, we have a long-running experiment with hot atoms in which we try to take all of this beauty of Rydberg interactions and implement it in a much simpler, maybe deployable system. With that, I'd like to thank the Rydberg Polariton team. Worked on that very, very hard in the past few years. So Gal Wiener and Tomer and Lee and Ban Kim and Eilon and Ariel, who recently joined us, and Sasha, who also joined the Institute recently. And thank you for listening.
Okay, thanks, Ofer, for a really fantastic talk. So first of all, I'll just pass along. It's not a question, but Dima Budker says amazing results. Congratulations, Ofer. And we have some other questions. So Nathan Shine was asking, should I have expected that the phenomenology of the total system can really be separated into pure two-particle interactions and pure three-body interactions, or should I be surprised?
I don't know if to be surprised anymore. We've been thinking about this for a year, trying to understand what we're seeing. And the fact that we can eventually more or less qualitatively get the results by kind of an ansatz of summing up the functions is not surprising to us anymore. These bound states exist, and somehow they occupy different regions in this three-dimensional space. So simply when you start with a wave function that is everywhere and quench it, it couples to whatever it can. So it couples to those bound states. In Efimov physics and three-body, few-body physics, those approximations are used a lot in this regime, kind of summing up bound states, summing up potentials, and summing up bound states. In a linear system, it does make sense to sum up solutions, and the final solution is still a solution. Yes.
Okay, maybe a related follow-up question from Caden. Is it possible to ever have three-body bound states at which, for parameters at which there are no two-body bound states?
Fantastic question. So this has been, this is like a footnote in the paper of Hans Peter, and then that was reiterated in some other papers. In principle, if you get to the point, probably close to the appearance of the second bound state, where the scattering length for pairs diverges, then you expect to see almost no effect from the two-body, from the pair interaction, and then three-body interaction should dominate. So yes, probably close to the appearance of the next bound state.
Okay, and then another question.
But maybe no, so sorry. But the comment Efimov physics, Brownian states that only have three-body bound states and not at all two, these probably would not exist in here because this system is genuinely 1D, and Efimov physics does not exist in genuinely 1D. If we could expand a bit the dimensions, for example, walking in the transverse dimension, then we get more dimensions, and this already has been predicted by Michael Gallans and others to produce Efimov states. Yeah.
Okay, question from some anonymous attendee. So in your simulations, it looks like OD goes all the way up to 100 or so. In experiment, how high can your OD actually go?
120. We hope for more in the future. At some point, it doesn't help you anymore, and ODB is much more important. As long as they go together, we accept everything that we get.
Okay, a question from YouTube. Is the three-body interaction also purely non-Gaussian and useful as a resource for continuous variable non-Gaussian quantum computation?
Not sure I understand the question, but there is no big difference between the three-body and two-body. So you could think about if you refer to what I mentioned as the genuine three-body interaction, I can think about this as a bit of a correction or a regulation kind of the two-body part. So the sum of the two bodies cannot express themselves fully. They are attenuated, regulated to some extent by the three-body part, but other than that, it's the same. Yeah. There are extra. I mean, the physics is not as simple. One thing that we should bear in mind, and this actually occupied a few follow-up papers, and very recently another one. There are not only dark polaritons in the system, but also at least 2 bright polaritons. And there could be scattering from the dark to the bright polariton that will introduce loss. This is this accelerates when we have more than 2 bodies, like 3 body. It's more of a problem in the dissipative case rather than dispersive case, but it's kind of a bit more rich. Yeah.
Okay, maybe we'll have one final question. So so far your medium is fairly like homogeneous, but you could imagine adding some additional structure to the atoms, like varying the density or something like that. Would that be interesting? And what would happen to these vortices? Would they sort of scatter? Would they, like we saw in the pool, would they kind of go away if you added some additional structure, or are they robust?
Mm-hmm. Yeah, that's an excellent question. So for the medium is not uniform. It's Gaussian, and it's Gaussian in all 3 dimensions. But it's slowly varying from the point of view of the photons. We have thought a lot about imprinting some potential landscape on the atoms, either the atoms themselves, simply trapping them in some structure, or imprinting this potential landscape by external light fields. Generating something. In particular, one interesting thing that you could do, if you imprint a Bragg grating, and a periodic modulation of the refraction index, then you would get a medium that acts as a mirror. But it would only act as a mirror for the blocked photons. The polaritons, because they experience no scattering and no dispersion whatsoever, no refraction index, they will just propagate. That will introduce reflecting photons that reflect each other. Turns into mirrors when they get close to each other, and that is an extremely rich possibility. So yes, making structures is very cool.
Okay, great. Well, maybe on that note, well, thank you again, Ofer, for a great talk and for giving it so late in the evening. And we'll end just by advertising the next Vamos in 2 weeks, which I believe is being given by Linda Young, who will be telling us about stimulated X-ray Raman spectroscopy with a free electron laser. So thanks, everybody. Hope you have good weekends. Happy Thanksgivings to those of you in the US who celebrate Thanksgiving, and see you in a couple of weeks.
Thank you, Shimon.
Yeah, thanks again, Ofer. That was great. Okay, I'll probably just end the webinar and YouTube, but it's great to see you, Ofer.
Great talk. Thanks so much.
Likewise,
Sorry
good
to
seeing you.
participate
Great
too much.
Thank you, guys. That was actually fun.
Yeah.
Yeah,
It's much more fun actually to be on that side than the other side.
For sure.
All
I think
right.
I enjoyed it too, though. I have to say it was fun for me too. So, all right, thanks a lot, Ofer. Good to see you. Let's catch up soon. Okay.